Hi there, algebra students. I wanted to just run through section 7.5 exponential functions so that you can see how we're going to go about this. So we're going to use technology to our advantage. So first of all, an exponential function is an equation where the variable is the exponent. Remember, back in section 7.3, we solved equations when the variable was the exponent, something like 2 to the x equals 8, and we'd make those the same bases. Now we've got something where we've got an x and a y, because that's how we do it with a graphing. We always have an x and y axis. And the form of this looks like y equals a times b to the x power. So we're going to go through some examples, but notice there are two constants, so a times b, and the x is only on the b because there's no parentheses around it. So y equals a times b to the x power. A is not allowed to be 0. It's kind of just one of those rules. B has to be positive. A doesn't have to be positive, but B must be positive, and B is not allowed to be equal to 1. So all kinds of fine print. Don't worry too much about that, but we've got to make sure we put numbers in place of those. So for example, I could have y equals 2 times 3 to the x power. So in that first example, the a is 2, the b is 3, and that 3 is being raised to the x power. In the second example, y equals 4 to the x power. There is no a, so it would be like multiplying by 1. So it would be like 1 times 4 to the x power, where the a is 1 and the b is 4. Same with the third example. I wanted to make sure I showed you. I know you avoid fractions, but y equals 1/2 to the x power. The whole 1/2, the fraction is being raised to the x power, so that's b. The a would be 1. So our graphs, we're going to see what they look like in just a minute, but our graphs can be going up, increasing, or going down, decreasing. If that b value that's being raised to the power is greater than 1, remember it's not allowed to be equal to 1, but greater than 1, it's going to be exponential growth, or it's going to be an increasing graph. You can think of it sort of like a positive slope, but it won't be a straight line. It's going to be a weird looking curve. If b is less than 1, it's exponential decay. So it's going to be getting smaller, it's decaying or getting littler. And for us to graph this, we are going to use our resources, the TI-84, to graph them. So let me just run through really quickly. I've got a short little video and I'm going to skip the middle part of it. So when we're in class, when you've got a TI-84 in front of you, I want you to graph the equation y equals 6 to the x power. So my a is 1, my b is 6, and that 6 is being raised to the x power. We're going to use that TI-84 to find the table of values, and then we're going to complete the table. Once we've got that table, then we will be able to go to a graph and graph it. So let me run through this really quickly. Sorry for the ad at the beginning. You know how it goes. Thank you to Mr. Roper. Okay, so we're not going to solve exponential equations, but we're going to graph them. So let me go over here to show you how we can get to our table of values. I think I'm going to be in the right area. Go back. All right. And play. So he's talking about that, but I'm really interested in this X column. I've got X values of -3, -2, 1, -1, 0, 1, 2, and it goes on forever. We could scroll up or down. But what I want to do is I want to grab some values. So I'm usually going to use mostly whole numbers. So for this one, I'd use -1 for the X, and then I'd put down that 1.667. 0 for the X, and the Y value is 1. 1 for the X, and the Y value is 6, and maybe a 2 and 36. Then I can put those on my table and I can go ahead and put those points on my graph and graph them. All right, so that's how we're going to graph. So when we're graphing exponential functions, we're going to use the TI-84 to graph them. We're going to use that second graph button to get to the table on the TI-84 so we can complete the table of values. And then we're going to answer the questions. So notice how this first example, it says graph y equals 4 to the x power. So we're going to use that and type that into the TI-84 right there on equation 1. We're going to complete the table of values and put the graph, those points on the graph so we can see what it looks like. Then we're going to find the y-intercept and state the domain and range. So we'll do that in class, but I wanted you to know that I'm not expecting you to do this and to know how to graph these just by hand. We're going to use our technology and our resources. So we'll do these together, but I wanted to make sure I mentioned how to find those and where those buttons are. We'll go through those. So let's talk about one more thing, identifying exponential behavior. So basically what I'm going to do is I'm going to give you tables like these examples that I've got. So exponential functions have a common ratio r. And the biggest deal about r is either we're multiplying or dividing. We're really looking for a pattern on our xy table in our y's. I notice on the first table, the x's increased by 10. So then I want to find out, okay, well, there's a great pattern. What about my y's? Is there a pattern in my y's? So the y values must multiply or divide, and that's what r is. The x values have to have a steady increase or decrease. Like I said, they're going up by 10 each time. I think all three of these examples do. So when I look at example 3a, we've got our x values going up by 10. What's happening to our y values? Our y values are getting smaller, right? So dividing, not multiplying. These guys are dividing by 2 in the x's. So our r equals 1/2 because they're getting half as big every single time. So I would say, yes, this is exponential behavior. So the answer is yes, because you would either say r is equal to 1/2, which tells me that you know that all of your y values are dividing by 2. So in the second one, in 3b, I look at my y first, looks great, or my x first, right? Increasing by 10, so it's a steady increase. My y values are getting bigger every time. So I either have to have multiplying or dividing to make this a yes. Looks to me like 15 to 21 is add 6. It looks like I'm adding 6 every time. So I'm going to say no, this is not exponential behavior because we are adding 6 to the y's, which means that actually if I graphed these, it would be a line. And letter C, is this set of data display exponential behavior? So I look, my x's are increasing by 10 every time. That's awesome. I notice my y's are getting bigger, so I'm multiplying. And if I play around with my calculator a little bit, I might figure out that this is multiplying, because it's getting bigger, by 2.5. The trick here, if you want to figure it out, is to take your y values and divide. So the second one divided by the first one. So 25 divided by 10 would give you 2.5 if you divided that out. So this one is yes, it is a exponential behavior because every y value gets multiplied by 2.5. And just check it to make sure I didn't change up the pattern on you, because you know me, I would be likely to do that. So I'm going to ask you to do two things in this section 7.5. I'm going to ask you to graph exponentials using a TID4, and I'm going to ask you, if I give you a table, an XY table, does it display exponential behavior, and how do you know if it's a yes or no? So, lesson summary. In your own words, describe how to determine if a function represents exponential growth or exponential decay. When we do some more of them, you're going to look at the graph. Otherwise, remember, it has to do with that b value, the number that's being raised to the power of x. And your practice problem, I put a practice. Does this table represent exponential behavior? Is it a yes or a no? Is there a common pattern in the y's that's either multiplying or dividing? If you want to check, you can always do like the second y value divided by the first y value, or the third y value divided by the second, the one prior to it, to see if you can get a pattern that would tell you multiply or divide. Remember, dividing by 2 is the same as multiplying by a half. That's why I switched that one. That's it for today. Thanks.